Introduction to SLAAC with DHCPv6. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with a focus on networking. Also, hit the bell icon to get notified of new videos. Today we are exploring one of the most important aspects of IPv6 networking, which is how devices automatically configure their network addresses and obtain network parameters. SLAAC, which stands for Stateless Address Autoconfiguration, represents a fundamental shift from how IPv4 networks operate. In IPv4, we relied heavily on DHCP servers to distribute IP addresses and configuration information. IPv6 introduces a more elegant approach where devices can configure themselves without necessarily needing a centralized server. The combination of SLAAC with DHCPv6 creates a hybrid model that gives network administrators tremendous flexibility. SLAAC handles the address configuration automatically, while DHCPv6 can provide additional network parameters that devices need to function properly, for example, DNS server addresses, NTP server information, and other options that SLAAC alone cannot provide. This hybrid approach leverages the best of both worlds. Understanding how routers communicate configuration information through router advertisement messages is crucial. These RA messages contain flags that tell devices exactly how they should configure themselves. The two most important flags are the M flag, which stands for Managed Address Configuration, and the O flag, which stands for Other Configuration. These flags work together to determine whether devices should use SLAAC alone, SLAAC with Stateless DHCPv6, or Stateful DHCPv6 exclusively. The beauty of this system lies in its efficiency. Unlike IPv4, where every device must contact a DHCP server and maintain a lease, IPv6 devices can generate their own addresses using the network prefix advertised by routers combined with their own interface identifier. This reduces network traffic, eliminates single points of failure, and scales much better in large networks. At the same time, DHCPv6 can still track which devices received which configuration parameters when operating in stateful mode, giving administrators the visibility they need for network management. DHCPv6 operating modes. DHCP version 6 can operate in 3 distinct modes, each serving different network requirements and management philosophies. Understanding these modes and when to use each one is essential for properly designing IP version 6 networks. The mode of operation is determined by the flags set in the router advertisement messages that routers send out periodically or in response to router solicitation messages from devices. The first mode is SLAAC-only, where both the M flag and O flag in the RA are set to 0. In this mode, devices rely entirely on RAs for all their configuration. They generate their own addresses using the advertised prefix and their interface identifier. The RA contains not just the prefix but also important information like the default gateway, which is implicitly the router sending the RA, hop limit values, and MTU information. However, SLAAC only has significant limitations because RAs cannot carry DNS server information or other options that applications need. This mode works well in simple networks where DNS can be configured manually or obtained through other means, but it is rarely used in production enterprise environments. The second mode, which is increasingly popular, is SLAAC with Stateless DHCPv6. In this configuration, the M flag remains at 0, but the O flag is set to 1. The O stands for Other Configuration, signaling to devices that while they should use SLAAC to generate their own addresses, they should also contact a DHCPv6 server to obtain additional configuration parameters. This is where DHCPv6 operates in stateless mode. The server does not assign addresses or track which device got which address. Instead, it simply responds to information requests from clients with configuration options like DNS server addresses through option 23, DNS search domains through option 24, NTP server addresses through option 31, and other vendor-specific options. This mode combines the scalability and resilience of SLAAC with the flexibility of centralized configuration management. The DHCPv6 server does not maintain any state about address assignments, which reduces complexity and improves scalability. The third mode is Stateful DHCPv6, which is more similar to how DHCP works in IPv4 networks. In this mode, the M flag in the router advertisement is set to 1, indicating managed address configuration. When devices see M equals 1, they know they must obtain both their addresses and all configuration parameters from a DHCPv6 server. The server maintains a database of address assignments, tracking which device received which address, and when the lease expires. Devices go through a 4-message exchange process: solicit, advertise, request, and reply. During the solicit phase, the client broadcasts a message looking for DHCPv6 servers. Servers respond with advertise messages, indicating they can provide addresses. The client then sends a request message to the chosen server, and finally receives a reply containing the assigned address and all configuration options. Stateful DHCPv6 provides administrators with complete visibility and control over address assignments, making it easier to troubleshoot issues and maintain accurate inventory. However, it introduces a dependency on the DHCPv6 server's availability, and requires more administrative overhead to manage the address pool and monitor lease information. It's worth noting that even when the M flag is set to 1, devices still need router advertisements to learn the default gateway address. Unlike IPv4 DHCP, which includes the default gateway in the DHCP options, DHCPv6 deliberately omits this information. The reasoning is that default gateway determination should remain the responsibility of router discovery protocols, not DHCP. Therefore, even in stateful DHCPv6 mode, routers must still send router advertisements, although these RAs typically have minimal information since the DHCPv6 server handles most of the configuration. Practical implementation and configuration. Implementing SLAAC with DHCPv6 in real-world networks requires careful configuration of both router and DHCPv6 server components. The configuration choices you make determine how devices on your network will obtain their addresses and what additional configuration they receive. Let's walk through practical examples showing how to configure these components correctly. On Cisco routers, enabling IPv6 routing is the fundamental first step. The command IPv6 unicast routing must be entered in global configuration mode to activate IPv6 routing functionality. Without this command, the router will not send router advertisements at all, and SLAAC cannot function. Once IPv6 routing is enabled, you configure the interface that connects to your IPv6 network segment. The IPv6 address command assigns an IPv6 address to the interface. Using the syntax IPv6 address 2001:DB8:CAFE:1:1/64 assigns a specific address with a /64 prefix length, which is the standard for IPv6 networks. The router automatically begins sending router advertisements with this prefix every 200 seconds by default, and immediately whenever it receives a router solicitation from a device. The critical configuration happens when you set the router advertisement flags. The command IPv6 other config flag sets the O flag to 1 while leaving the M flag at 0. This configures SLAAC with stateless DHCPv6, meaning devices will generate their own addresses but contact the DHCPv6 server for additional options. If you want to use stateful DHCPv6 instead, you would use the command IPv6 managed config flag, which sets the M flag to 1, telling devices to get both addresses and configuration from the DHCPv6 server. You can also adjust the router advertisement interval using IPv6 RA interval, though the default values are usually appropriate for most networks. The minimum interval between unsolicited RAs is typically 200 seconds, but you can reduce this if faster detection of network changes is needed. Configuring the DHCPv6 server involves defining a pool of configuration options that will be provided to clients. For Stateless DHCPv6, you create a pool using the IPv6 DHCP pool command followed by a pool name. Inside this pool configuration, you specify the DNS servers with DNS server 2001:db8::53, where 2001:db8::53 is the IPv6 address of your DNS server. You can specify multiple DNS servers by listing them, separated by spaces. The domain name command sets the DNS search domain. For example, domain name example.com. This allows devices to perform DNS queries for host names without the full domain name. You can also configure NTP servers using vendor-specific options or standard DHCPv6 options, depending on your server implementation. After defining the pool, you must apply it to the interface where clients will be requesting configuration. Under the interface configuration, the command IPv6 DHCP server pool name associates the defined pool with that interface. The DHCPv6 server will then listen for information request messages on this interface and respond with the configured options. For Stateful DHCPv6, the pool configuration is more extensive because you must also define the address pool. The address prefix command within the pool specifies which addresses can be assigned. For example, address prefix 2001:db8:cafe:1:/64 lifetime 86,400. The lifetime value of 86,400 seconds means addresses are valid for 24 hours before needing renewal. On Linux systems acting as DHCPv6 servers, the most common implementation is ISC-DHCP server or DNS mask. The configuration file for ISC-DHCP, located at /etc/dhcp/dhcpd6.conference, defines the DHCPv6 behavior. For Stateless DHCPv6, you include the line option dhcp6.info refresh time 21600, which tells clients how often to request updated configuration. In this case, every 6 hours. The subnet 6 declaration defines the network segment. For example, subnet 6 2001:db8:cafe:1:/64. Within this subnet declaration, you specify configuration options. For example, option dhcp6.name servers 2001:db8::53 for DNS servers, and option dhcp6.domain-search-example.com for the DNS search domain. For Stateful DHCPv6, you add a range 6 statement. For example, range 6 2001:db8:cafe:1:1000 to 2001:db8:cafe:1:2000, defining which addresses can be assigned to clients. After modifying the configuration file, restart the DHCPv6 service using systemctl restart ISC-DHCP server 6, or the equivalent command for your distribution. Verification and troubleshooting require examining both router advertisements and DHCPv6 operation. On Cisco routers, the command show IPv6 interface displays interface details, including whether RAs are being sent and what flags are set. The output shows you the RA interval, whether the M flag and O flag are configured, and other ND parameters. To see active DHCPv6 bindings on a stateful server, use Show IPv6 DHCP binding, which displays all currently leased addresses, which client DUID received each address, and when the lease expires. On client devices, Windows uses NetSH interface IPv6 show addresses to display all IPv6 addresses and their configuration method. Linux systems use IP6ADDR show, which shows whether addresses were obtained via SLAAC, DHCPv6, or configured manually. To see received DNS configuration on Linux, examine /etc/resolve.conference or use resolvect-l status on systems using systemd resolved. Thank you for your attendance. Please consider subscribing to the channel and liking this video.